Let's take that principle and that approach for determining shape factors and apply it to those two bridges that we saw at the beginning of the class, right? Let's say it's a steel truss bridge. You have a span L. It has to be supported by both ends. Because you know how much material goes into building that bridge, you can find what its mass is in tons. And typically, these designs are designed for stiffness, so that the central deflection under self weight is 1/300th of the length. That's a typical construction engineering, bridge engineering shape factor. I think of my uncle who passed away recently, who was a bridge engineer for the railways in India. So now, given this information, we have to compute the shape factor of the bridge. And we know we can compute the shape factor if we know all these terms on the right hand side, right? Stainless steel or steel, let's say, rho and E is known. We can know C1 for this type of a situation. We are given mass, we're given length, and we are given stiffness offered as a function of the length. So stiffness is given by this term where M and G and L are given. Knowing these terms, we can go ahead. The only thing that's directly missing is C1. And if we know that, we can go ahead and do this, right? Let's take away how we apply this for three different bridges built over the last couple of centuries, starting from 1857 towards the middle of the previous century. A lot of our infrastructure, you must have repeatedly heard, needs updating. Yes, we did have a couple of new bridges built outside of Louisville over the Ohio River, but this is not the case all around the country. Many of these bridges are really old. So we have M, we have L. Because it's steel, we can look up rho and E. What is C1? Do you know what is C1? How you can find that for these kinds of trusses? So if you Google the names of these bridges, the leftmost is the Royal Albert Bridge. The middle one is the Carquinez Strait Bridge in California. Chesapeake Bay Bridge in Maryland. Driven over that many times when I was living in the Northeast, going back and forth between New York and DC, and eventually from Pennsylvania to DC as well. So, how do we use this equation? We know the density, we know the modulus, and C1 for a uniformly distributed load as an assumption is 384 by 5 or about 76.8. Okay. We just need to make sure that all these funky units in tons and so on and meters are all brought together in a similar manner, right? So that you can get newtons, and then you can get some simpler units for phi b. So at this point you have everything you need. You have C1, you have M, you have L, you have G, you have rho, you have E, you have consistent units. And if you go ahead and look at estimating the load, which is a self weight of the bridge, and you have this term over here, area, you can compute phi b. So you can see that as time passed from mid 1800s to mid 1900s, this shape efficiency factor has also gone up. Another way, in a simpler manner, to indicate this is the load bearing capacity while meeting with deflection limited designs has gone up. The way we build bridges, the designs that we build it, the materials that we build it from, all have increased tremendously. Okay, so this is something that is a takeaway. The next question I have for you is, do you remember what was the maximum shape efficiency factor listed in that earlier table for steel? Are all these bridges within that maximum shape efficiency factor or not? So if you see, for bending, for structural steels, the maximum is 65. So we saw in the first case, it was for the Royal Albert Bridge, In UK, you are well within this maximum. You are approaching this maximum for the California Bridge, and then for the Chesapeake Bay Bridge in Maryland, you exceeded it. Question for you is, how do you exceed this maximum? It means, compared to the shapes that we looked at during the shape efficiency factor section, we are dealing with much more complicated structures. And by having these kinds of hierarchical structures, it is possible to make a more structurally efficient bridge, in that for the same amount of materials, you can have a much higher compliance to meet the constraints for stiffness and load.